Okay, hello everyone. We start the session, open the session. First of all, any questions from yesterday? No? Everything was crystal clear? Yeah? Okay. So today we're going to do an exercise, so we will check really if it's crystal clear or not. The topic for today is again continue, and I hope to finalize this topic on networks. Okay, how do you deal with networks? And we will see a bit why they are so important. You have an idea that really a production system is not just one well, or it's not just isolated number of wells, but you have actually to see the interaction that these wells have in between them. Okay, and what is actually the system that you have from the wellhead all the way to the processing facilities. So we will do an example today. Then I'm going to talk to you about how do we set the rate of the wells in a network system, and then we are going, if we have time, we are going to see about downhole networks. We don't not only have this kind of issue in surface, okay, in pipelines and flow lines, but we also have this issue in inside of the wellbore in some cases, and that can cause also some pain. And then I hope to have time to talk about allocation. Okay, so let's see. It's kind of a bit ambitious, but we will try to leave at 5. Okay, I won't keep you more than that. Okay, so one person, I just wanted to make a comment. If you remember this comment from last class. I told you that if you put 2 wells, a system of 2 wells, each one of them has a choke, 2 gas wells, and then they go to a junction, and then they produce to a separator. Okay, I told you that it was possible to get some kind of operational diagram where you have 3 points. Okay, and this is just natural flow. The 2 chokes are open, and this is fully open choke 1, and choke 2 is closed, and this is fully open, choke 2 fully open, and choke 1 closed. Okay. One person was asking that when do I get the maximum production? Okay, optimization. So when do I get in this system? Maybe there is a choke opening. Okay, I think that maybe trivial. Okay, the 2 chokes open, that's the maximum production. But maybe I find there is a particular setting, let's say this choke 30% and this choke 50%, that gives you maximum production. So how can I see that from this plot? Okay, so one way to do it is that you have actually for this line, okay, the combination of these 2 points, the sum of them is actually the total rate, okay, the total gas rate, right? So if we can also plot a second diagram that has to be kind of 3D. So for every combination, we're going to do it only on the line, okay? We don't want to touch the points, even though that might be an issue, okay? There might be, for example, that the maximum is located someplace here. Okay? But for now, we are going to just sorry. Okay. So we have Q1 and Q2 here, and we have our area. And then we say the total production at this point is exactly Q1, right? I just have to take this distance here, and put it on the vertical axis. If on the vertical axis I have the total production, right? So I do that, then I get this point, okay? Then exactly on this point is just the sum of the 2 of them, so I have to actually sum this value plus this value, and that's why I get the point in the center. So I'm going to make it a bit smaller, or a bit, yeah, I'm going to do a trick. Okay, and I go exactly on this point where the 2 are fully open, I put the sum of the two rates, and then I will get a value, very high value like that. And then this point I do the same when choke 2 is fully open, choke 1 is closed, so I get again this point. And this is how the surface of total rate does, okay? And then I need one more point to create a kind of to see how it looks like, and that point is at the origin. If you remember, at the origin the two wells are closed, so then I connect them something like this. Okay, actually these two lines, they can be continuous because we are looking at the thing from the front. Okay, and the dotted lines, they are kind of the lines on the back. Okay, so you see that actually the surface is something like that. Do you see that? All of you have enough imagination, 3D view to see that? Yep. Okay, so you see very clearly that that this is the point of maximum production for this particular case. Okay, we just open the two chokes fully open, and then I get maximum production here. But what happens now if my figure, instead of being like that, is like this? What someone was asking last time. What happens if I get actually more production? Okay, that actually the sum of these two rates, Q1 at open choke and Q2 at open choke, actually this Q1 star is greater than Q2 plus Q1 at the, how should we call it? We can put a 1 here. Okay? If that happens, it tells you actually that it's better just close completely well 2. Okay? Because you will get, then the shape won't be like that, but the maximum will be located here. You see that? Yeah. So as I told you, we are going to have a separate session on optimization where we are going to discuss this issue more in detail. But just to let you know that not all the time when I just open the two chokes maximum, then I get full production. Okay, might be happening that this will actually, in this case, what is this telling you? That well 2 actually doesn't produce much, but creates a back pressure to well 1. Okay, it kind of inhibits him from producing more. When you remove the well slowly from the equation, you take it away, you close the choke, okay, until it's fully closed, then well 1 has enough space in the pipeline and can produce to its full potential, okay, to its full flow. So keep that in mind. In this simple case, I didn't plot, didn't make you the 3D plot, but I think it's going to look something like that, just surface and then declines when you reduce the rate. But you might have also this situation when one of the wells is maybe more powerful than the other, and then it makes sense to choke the weak well, to choke the strong well, and to give priority to the well that has higher production. Okay, we go back to our Zoom 75. So let's make an exercise to address kind of all of these questions or all of these cases that we discussed last class, okay? Just natural flow, then we are going to discuss choke calculation, and then we're going to talk lastly about boosting. What happens if we install a small compressor, okay? So Excel exercise, and you have it on its learning. I appreciate if you want to do it, at the same time, so that's okay if you brought your laptops. It's called network 2 gas wells, okay? Yeah, and this is my system. Sorry, I didn't put all the dimensions, but I made the calculations with this equation that I showed you. I think this dimension is 5 kilometers, and this is also 5 kilometers, and this is a 3-inch pipe. Okay, and then you have in this long section, I think I put this is 10 kilometers, and this is a 4-inch pipe. The separator pressure is indicated in the exercise. It's actually 28.6 bar. It's a dry gas, so we can use our famous our good equation, dry gas equation, and they are producing the wells have, I think it's 3-inch ID also, I think. And one well is slightly shallower than the other. I think one of them I put 2,000 meters, 2 kilometers, and the other one I think was 1.5. Okay, but all the data is given here on the sheet. Where is it? Here. They are connected to the same reservoir, yes. Okay, that was missing here. Very good point. They are producing from the same structure, from the same reservoir. Okay. So let's see if we have enough data to do our calculations. Okay. First, we have to go from the bottom hole. Okay. Let's see if we have enough information for the IPR. We know the dry gas equation, C and N. Actually, also one comment that I want to make. This gas equation that we are using is usually for low pressure. Okay, when you have high pressure, you cannot use the pressure right away on the equation, but you have to use a pseudo function. Okay, M function. How many of you have seen that before on your courses? 1, 2, 3. Yeah, if you want, I can put some references on its learning. Okay, so we have C and N, so that seems to be enough. Dry gas wells. Then we go to the tubing, so we have CT and S, and you see the values. They are slightly different because they are completed in different regions. The permeability, local permeability is slightly different. Yeah, I think the diameter I put the same. I think. Then you have a flow line, 5 kilometers all the way, reaching to, and this point is what we're going to call a junction, J. Okay. And then from there we have a pipeline. Actually, we put it here to use the space. We said, okay, here we have well 1 and well 2, all the data. But then for the flow line, I'm just putting another element. Okay, and I say pipeline has 10 kilometers. Okay, and this is the resistance. And it's horizontal pipeline. Let me just put that here. Okay. So how do we solve this problem? Let's say the first task is to calculate the natural equilibrium point of the system. Hydraulic equilibrium of the system. And we are going to assume that there is no choke. Remember, I told you two things, okay? Well, not two things. I've told you many things, but one of these things was that the element, we can put it actually in the model, okay? The choke or the model of the pump, we can put it in the model, or we can just take it away and use it for design, okay? In this case, there is no choke installed, or if the choke is installed, it's fully open, so we can neglect it. And we want to calculate how much each well will be producing if I operate this case. So anyone has any suggestions how to make this calculation? We said here we are going to take the problematic point, okay, which is the junction, okay? In the junction, so what we said last time, I said I can calculate the pressure co-current. We have to use another color, this one. We have to calculate the pressure co-current all the way to the junction, okay, from the bottom of well 2 all the way to the junction. We have to calculate again from the bottom of well 1 all the way to the junction, P junction, and then we calculate counter current all the way to the junction. And we are going to get 3 values, okay? And then we have to change the rate of each well until, or we can also change P junction, but we are going to change the rate of each well until these 3 pressures are the same. Okay. So let's begin to do that on our Excel sheet. So we have here, so where do we start? Let's try to guess, we like to guess with pressure. So let's put P bottom hole, okay, flowing bottom hole pressure. And initially I'm going to put a value, let's say very high, okay, 110 bar. Okay, this value, all the values that are in red is because it's an input that I have given to my Excel sheet. These values that are in violet, they are because they will be used by the solver to adjust, make sure that all of these pressures are the same. Okay, so that's why I put it violet. Okay, so we have the pressure, and now we can calculate the rate. So for that I use my IPR equation, IPR QG. Okay, I don't remember exactly the order of variables that I have to use, so I go back to my function and I say, okay, my C, back pressure coefficient, back pressure exponent, sorry, is this one here, okay? For we are working in well 1, right? Yeah, forgot to put the header. Okay, I want to calculate the rate, so I say the C of the well, the N of the well, the reservoir pressure. I need that to calculate the rate, and then I need the flowing bottom hole pressure. Okay, gives me a value of 25,000 standard cubic meter per day, which you have to tell me if that's a reasonable value or not. And then I just drag it. The nice thing is I don't have to block any cell here. I just can drag it down, and then it's going to take the properties of well 2. Everybody okay so far? Yeah. So now I'm going to progress even further. So far I have been all the way to the bottom hole, and now I'm going to move to the wellhead of both wells. So I say PWH is in bar. And here, which equation I have to use? I have to use tubing, and tubing we had P1 or P2. We want P2. Okay, so tubing P2. Don't remember again all the orders, so we use the tubing coefficient, we use the elevation coefficient, we use the inlet pressure. The inlet pressure to the tubing is the flowing bottom hole pressure, and the rate. Okay, the rate I just calculated. And here I have a small mistake, okay? The things that I calculated, they should be in blue. So let's put that in blue.
Yeah, what is P1? It's PR?
P1, what is entering into the tubing? What is the point there? Flowing bottom hole pressure, okay? Remember, all the time I can bring my system back to a simple well separator system, where I say this is my wellhead, this here is my flowing bottom hole pressure, and this is my reservoir pressure. Okay, so far we have come from here to here, and now we are going from here to here. Okay, let's see if that makes sense. 110, I have a relatively low flow rate, so I get only 7 bar delta P in the tubing. Also the rate is very low, and then I go here and I get 104. Then after that I have to move even further. Now the next point is going to move at the junction. Okay, I have to calculate the available pressure of well 1 and the available pressure of well 2 at the junction. For that, which equation do I have to use? We can assume that the flow line is just horizontal. Okay. So P junction, that's in bar also. Then I say that's going to be equal to, the equation was line, I think, line P2. Let's see, it's using coefficient of the flow line. Each one of them has its own flow line. Then the inlet pressure to the flow line, that's going to be the PWH, and the rate is this one, okay, and 102. Also not many, actually there are almost no losses between the wellhead and the junction. Maybe the pipe is too big. Okay, then we drag it down and we have line P2. Everything goes okay so far, and that's where I stop up to this point. So let's take a screenshot of that. up to that point here, I stop my co-current calculations. Okay, I have done all the calculations that I need co-current. Up to this point, they are co-current calculations. Okay, so I stop there. Now I have to calculate counter current from the separator to that junction. And if you see, it's quite practical because I can put really in the same for the pipeline, I can put its P junction. Okay, so for that, what do I need? The pipeline is carrying the rate of both wells, so I have to put here one cell that is the sum of these two rates. Okay, so I have the rate, I have the inlet pressure, I have the resistance coefficient, so I can calculate line P1. Line P1, C flow line, P2, and the rate. Everyone okay so far? Yes? So you see a big difference. That means, and there is also not much pressure loss in the pipeline. That means that the well might be producing more. Okay, more than 25,000. Might be producing actually much more. Okay, so how do I make now in Excel that all of these three numbers are the same? Anyone has any idea?
I did it yesterday, actually.
Yeah, but you already know the answer, so you are banned from participating. Yeah, I'm just looking all the time for new ideas. I hope that there is someone, mathematician or something that tell me no, there is a better way to do it. Okay, no ideas how to make all of this? Remember that the solver only takes one cell, okay? So I have to put everything, try to find a way to compound everything, to reduce everything to one cell. So my proposal, what I have been doing all the time so far, but you might have a better proposal, is that here I'm going to put P average, and I'm going to calculate the average of these three cells. Okay, wait, now I create a column that's called error, and this error is going to be cell PJ minus PJ average squared. Okay, then this one again, the same thing PJ1, PJ2, PJ3, okay, squared, and then at the end here I put the sum of all of these differences, and then I have one cell. Okay, I can tell the solver, please change solver, that's my objective. Okay, drive that cell to 0 by changing these two, okay, the flowing bottom hole pressure, which will be equivalent to changing the rate. Okay, so let's do that very quickly. We create here P average, that's also in bar. Okay, these three, and here I'm going to put the error, and this error is going to be in bar squared, and this will be equal to the pressure junction 1 minus this average that I'm saying. Okay, that's one way of doing it. You might have a different way. I have to lock this cell because I want to drag it down, and I want that cell, the average, to be all the time the same cell. Okay, so function 4 squared, actually that's a big number, big number. Okay, let's see if it's working. Okay, and then I can put here one cell that I say total error, and this will be the sum of all of these differences. Okay. That should be also in blue. Okay, so I want now to use my solver to say solver, pretty please, that will be the equivalent to solve the whole system of equations. Drive this cell to 0 by changing these flowing bottom hole pressures. Okay, I'm going to save, okay, because I don't want to have any problems. So let's try now with the solver. Solver, oh, someone was doing this before. Okay, you want that cell to drive it to a minimum. Everything is squared, so the minimum that it could have is actually 0. That's what I want. Okay, by changing these two cells, and these two cells are actually I6, I7, are the flowing bottom hole pressures. And then I say that these pressures, they have to be smaller than the reservoir pressure. Okay, let's take that and just take those as snapshot. Anybody try to solve it so far? No? Okay, so this cell is actually this one here. Yeah, I didn't put the flowing. This is PWF1 and PWF2. And this condition here is that PWF1 has to be smaller than P reservoir 1, and PWF2 has to be also smaller than P reservoir 2. Okay, so let's try and say solve to see what happens. Okay, problem. Okay, let's see what is the problem. Says found an evaluation error in one of the target cell. Okay, so let's see actually what happened. It was testing values that are actually okay. So it was testing a value that was too low. Okay, so with that it got a very high rate, and with this very high rate actually this function became undefined. You see that? Okay, so this is actually exactly what we were discussing last class, that you assume a value, the solver comes and assumes a value, and then that value might be undefined because you don't have enough pressure to reach to the wellhead. Okay, but the solver stops, it cannot continue. So let's again, you know, I'm just making some nice notes for you. I could go a bit quicker, but okay, so PWF is too low, then that causes that the rate is too high, and if the rate is too high, then PWH is negative. Okay, because of the issue that I told you with the square root. Okay, if you remember the equation, how was it? CT PWF squared over ES minus PWH to 0.5. So from this expression we clear P wellhead equal to the square root of Q over CT squared was like that, right? Okay, so actually this value is too big. Okay, so we're getting an error value.
When you were defining the parameters in the solver,
Okay.
why did you not constrain that all these PJs will be equal?
No, that's I'm doing because I compounded all of them in this cell. Okay, I'm just calculating a P average, and then I'm saying that the difference between the junction pressure of each one of them minus the average also has to be it has to be 0. Okay, the sum of all of them. That I think I put here. Okay, you create an average junction pressure, then you say that the junction pressure calculated from well 1, calculated from well 2, and calculated from the pipeline. Then you subtract from this average pressure. Okay, you square it because you want all the time to be positive, and then you sum all of them. And this is actually the objective that I'm giving the optimizer. Okay, and this is a way to reduce all of these conditions, because otherwise I will have this equal to this and this equal to this. I will have two conditions. In this way, I'm reducing all of these into one cell. Okay, and that's one way to do it. Those of you might have another idea, you can test it to see if it works. Okay, actually I would like to have another idea, less complicated.
I also constrained this PJ and it's not violating the.
It's not?
Yeah. If you constrain this, all PJs are equal.
Okay, but then what do you maximize or minimize?
I calculated PWF.
You are maximizing PWF?
Minimizing means calculating the PWF.
Yeah, but that's, I'm guessing, with PWF,
Yeah.
right? So what do you put here in this cell?
I'm checking is the average error. Yeah, it's the same.
Oh, it's the same, but you have here one condition that the pressure should be equal. Okay. Okay. So it's equivalent. Yeah. But you didn't get this error. Okay. So to avoid this yeah, we can maybe go back to your solution later. But to avoid this, what I propose is we started with 100, okay? And we didn't have any problems. Okay? I propose, let's say, maybe the result, okay, we see here that actually the difference is very high. But if we begin to reduce this pressure, okay, let's put, for example, 80, okay, that error begins to reduce, okay? Every time the values begin to be more and more similar. So let's try now with, I think what I tried was 50, okay, that they become more or less similar. And now I can try to execute the solver for this problem, okay, and actually now it converged. Okay, so it's very important the initial seed that you use, or maybe what Bilal was using, something else to help the solver not to have this error. Okay. So what I have done here, this is the final solution that I have done, is the initial values, they were actually lower than what I put originally. And by making them lower, I'm making them closer to the final solution. I think we tried 50 and it's 38, so it's closer than 100 to 38. Okay, so that's the that's the final solution, and I using a starting point PWF1 equal to PWF2, that was 50 bar. So we got the convergence. Okay, and it tells you actually in this case you can see that there is one well that is actually weaker than the other. That one well produces 100,000 standard cubic meter per day, and the other one produces close to 50,000. Okay, so almost twice the production of the other well. Okay, so we finished now with this part. What happens now if we want to make choke? If I want to produce a specific rate from these two wells. Okay, I say that, for example, well 1, QG1, it has to produce 80 e to the 3. Someone told me my depletion strategy has to be this one, 80 e to the 3. And number 2, we can say maybe 30,000. So I say fixed production rate. One thing that is important to note is that when you don't have any controllable element, you don't have any element or any equipment that you can change, the solution is unique. Okay, this is what the system is going to produce, period. Okay, doesn't matter if comes, reservoir engineer makes, put some holy water and they improve it somehow, doesn't matter. That's what the system is going to give you. You're bounded by that. Now if you come and you say I have chokes, I can regulate, or I have pumps, or I have compressor, then that's a different story. Then I can get any other combination of rate. Well, more or less. But when there is no adjustable equipment, no gas lift, no pumps, no chokes, or no adjustable chokes, then there is a unique solution. And that's what the reservoir engineer has to understand. When they go to you and say, can I produce this rate? You say no, and actually you have to produce this combination. There is no other alternative. Unless, and then they're going to tell you, okay, we have budget here, out, behind the below the carpet, so here, please install now a compressor, and then, we can make your life happy, okay? But if that doesn't happen, then they are not going to give us money, okay, the reservoir engineer. Okay, so let's see now, how do we do in that case? So I'm going to just erase, okay, that. So before I leave this part, is clear this example? Yeah? Okay. Because you will have to work with that with the exercise, so it should be very clear, yeah?
So, for example, we do it analytically. We will do the same thing, what we have done in the Excel sheet.
Analytically, you have to pose the system of equations, okay? You have to put them in a matrix, like I think I put the notes on its learning. Okay, analytically you have a system of equations. Actually you have to write each one of these equations. You have to create a vector that has all the functions, all the equations, and then you have to calculate the gradient of that function. You have to have the function, and then you have to have the gradient, and then you have to give, going from an initial condition that in my case was 100 bar, or has to be 50 bar, then you have to evaluate the gradient, the function, and find out the next point. Okay? Then after that you repeat, do again the same evaluation, gradient and function, move to the next point, and you repeat that process until you get convergence. Okay? You see, we are avoiding all of that complication by using our dear solver. Okay? And that's something that you have for free. Okay? It's, well, not for free if you have Excel license, but luckily here we have a Dentenu. Okay, so now any other question? No? Okay. We go with rate now. Let's say we are going to give now the rate, standard cubic meter per day. And we said that this well has to produce, this one was the good well, okay, we know already. So this well, we say we want to produce 80, and that's going to be an input. Okay, so I'm going to put it in red. And this one was 30, I think, was it? No? And again, I'm going to put it in red because that's an input. So now I calculate from this, I gave the rate so I can calculate the flowing bottom hole pressure. So PWF bar, and here is IPR PWF, and let's see what this one needs. The C of the reservoir, N of the reservoir, reservoir pressure, and rate. I drag it down. So now I have to progress even further. I have to go all the way to the wellhead. So PWH okay, in this equation, what equation do I have to use? Tubing P2, the same equation that I was using before. P2, and this one needs the CT DS, the inlet pressure, that is the flowing bottom hole pressure, and the rate. Okay, actually again I don't have much losses in the tubing. I drag it down, also no losses at all. But then where do I have the choke? The choke is at the wellhead, okay? The choke is, if you look at my drawing, I have to go back. So actually the choke is here, is part of the wellhead. It's a valve that is kind of built in the well, okay? So in this case, that's where my calculations have to stop, okay? My co-current calculations. Now I have to make my counter current calculations from the separator to the junction, and then from the junction to well 1 and well 2, okay? Because that's where I have, that's my point of interest. Remember, for equilibrium it's very important, where is my point of interest? My point of interest, for this case, let me just copy that figure. It sounds kind of stupid, but for choking, My point of interest is where the choke is. In that case, my choke is here, so I have to make co-current calculations from reservoir to flowing bottom hole pressure all the way to wellhead, and then I stop because that's where my point of interest is. Okay, actually I have 2 points of interest, these two, and then counter current I say from P separator all the way to P junction, and then from P junction I have to make one calculation to calculate P wellhead required, okay, or if I put the choke, that would be P downstream the choke, or P downstream the choke, and I have to calculate required 1 and PWH required 2. Okay, so let's do that, and then we take a break. So far here we have done our co-current calculations. Now I have to calculate P junction, okay, and P junction luckily it's only 1. So here I say I have to calculate again the sum of the rates total, and we say sum of rate 1 and rate 2. That should be in blue, and then here the P of the junction is equal to, that's line P1, okay, and here I need the flow line, the P2 pressure, and then I need the rate, okay, that the rate is this one. Actually this rate is better to put it up here, P1. So I need this coefficient, this pressure, and this rate. Okay, makes sense. Okay, it's all the time greater than this pressure, so it makes sense, and you have only 2 bar. Now I don't have to calculate like in the other case any other P junction. In this case there is a unique P junction, because now I have to move even further and I have to go and calculate. This one will be P wellhead available, and I have to calculate here P wellhead required. And then what equation do I use here? Again, line P1, and line P1 depends on the C flow line, depends on the outlet pressure, that the outlet pressure is P junction, okay. I block it because I don't want that to change, and the rate is just the rate of that line, which is the rate of well 1, which is this one, correct? I can drag it down, nothing will happen, and now I can calculate delta P of the choke, and that one is going to be in bar, and I say this is equal to the available minus the required. So that tells me if I want to deliver exactly this rate, 80,000, then I have to put a choke of 30 bar, and in number 2 I have to put a choke of 50 bar, 52 bar. What happens if I let's say want to produce more? Let's say I want to produce from the second well, I want to produce 50,000. Okay, so let's see, these are the results. This is the chokes. To get the desired rate, okay? Choke delta P's to apply to get the desired rate. Now if I have I don't know much, okay? I just say I don't know how my system behaves. I haven't run the equilibrium, but I say I want to get from this well 50,000, okay? And the nice thing about this sheet is that you can change it. So actually it tells you that the delta P of the choke is -2. Actually, you cannot, that rate is not feasible, okay? You will have to, if you want to get that rate, you have to put a compressor at the wellhead. You have to put something that gives that 2-bar pressure in the to the well, okay?
In this sheet, if we calculate the rates by constraining delta P choke 0, then we will get the same results as
Exactly. Okay, very good observations. If we put here now delta P equal to 0, we set up a new solver saying, solver, please drive these two delta P's to 0 by changing these two rates. We will get exactly the equilibrium rates. There is only one combination of rates. With fully open choke or with no choke, there is only one rate combination. Okay, so let's take a break and we come back with a kind of a bit trickier case about boosting. Okay, about compression. Okay, so now let's see, let's look a bit, these two cases that I mentioned, that you have natural flow and then you're fixing the rates. You will use that. I will publish a new exercise this week, so everybody's happy. Say, yes, exercise. That you will have to use these two things, okay? You will have to do natural equilibrium and you have to use actually choke calculation. That is also closer than the snow white exercise that we have done. Usually you have a network and usually each well behaves a bit different. So you will use actually these two things. And compression, we deal with artificial lift and boosting at the later stage, but I think it's important to bring it up here to close completely the issue of networks. So imagine that at the later stage, initially we didn't need any compression, okay, because there was enough energy in the reservoir to produce. But when the pressure becomes 40 bar, then I'm thinking about installing a compressor and have to change slightly the layout of the system. I have only one compressor, so I will use it like that. In the junction, I will cut the pipe and actually install a compressor module, and then I put the discharge. And then I want to calculate, I want to fix a rate. My main goal here is to fix the rate. Fix the rate. Fix the rate. And I want to estimate, just like in the case of the choke, the delta P of the compressor. Okay? Let's say you want to get certain production from these wells, and then I see, when I come to the manufacturer with this delta P and this rate, they can tell me more or less which size, okay? And if I'm buying, I say, okay, I want to know if I have to buy a $20,000 compressor, $50,000, $1 million compressor. I want to know. So I want to know if for what I want, if I, how much do I have to pay? So in this case, so let's plan a bit now before we go to Excel the strategy. What do you think? First, we have to know how much we have to produce, right? What has to be the total rate? So let's do that first. So we put here 40. First, we get rid of all of that. Okay, and we put here 40 bar. 40 bar. Okay, so what would be a good rate to put, do you think? Huh? For that reservoir pressure, yeah. What is a realistic number?
500.
How do you do it? How do we have enough information to know this from to do some calculation to see how we can estimate this number? How much we can get from this system?
Yeah, we PWF.
Okay, we have the IPR. And then if we say PWF, for example, is like 8 bar or something like that, then we get more or less kind of the maximum rate. Actually, the maximum rate we get if we put 0, we put vacuum in the front of the perforation. Okay, so let's do that just to get an estimate. So we say PWF in bar, and I'm going to put, for example, 0, just we know it's not possible, but for the fun of it, because after that I have to go and overcome all the pressure loss in the tubing. Okay. So I get here QG, and that's in standard cubic meter per day. And if I use that flowing bottom hole pressure, IPR QG, then this equation is using C, is using N, is using reservoir pressure, and is using flowing bottom hole pressure. Okay, so I get 19,000 and 10,000. So that's really the maximum rate that I can get. I can get around 29,000. Okay. So let's say that. So how much, what is the maximum rate? That I can get, okay? So for that, I know that I have my IPR, PWF versus Q, and does something like that. So I just come here with the minimum flowing bottom hole pressure that I think, okay? It could be 1 atmosphere, it could be I use 0 bar, which is not realistic, but just to get this point in the curve. I just want to get this number to see how much is it. So this point for well 1 is 19,000, and for well 2 is 10,000. So let's see, you know, I'm kind of a bit ambitious, so I will say I want to produce 28,000 from this well. Okay, let's see if that's possible. So let's say for startup, I say I want to produce. Okay, it's quite high, but at least it's realistic. Okay, it's maybe something that I might get. If I say I want to get 50,000, you already know that this guy is crazy. He doesn't know what he's talking about. Okay, because no matter what you put, what pressure you put in front of the perforation, you will never ever get 50,000. Okay, I want to produce 28,000 standard cubic meter per day. So if I fix the rate, exactly the same thing, okay? Now where do I have to put my equilibrium? In my system that I showed before. Where is my equilibrium point?
Separator.
No, where is my element, my component that is causing problem disruption here in this example? The compressor, okay? So that's where I decide to put it. So I say these two wells, okay, they join in a junction. These wells are open choke, or they have no choke. Remember that chokes, I showed you, did I show you pictures of a choke? No? I did? Cage choke? Did I show, I'm kind of crazy now, did I show pictures of a choke in class? Yeah? No? How many says yes? How many say no? Okay, maybe I'm half crazy, I don't know. Yeah. So there are some chokes that are adjustable, okay, that you have something that you can adjust and change the position, and there are other chokes that are fixed, okay, that are called bean or positive chokes. It's a restriction that is like that, okay, and then you cannot adjust, but to change the delta P, you have to go and change actually the whole thing, the whole cartridge, okay, it's like a cartridge. So you change that, and if you want, for example, with depletion, then you change and put a smaller and smaller and smaller, okay. The adjustable is just what the figure that I showed before, okay, and then I can change by pulling this up and down. I can change the opening, the losses, okay. A bit. I will try to bring some pictures after. Okay, so we say, so the comment was that open choke means that maybe this system was operating with a beam choke, with a positive. This is called a beam choke, or also called a positive choke. Okay, And maybe they were just changing time, and at the end they just leave it open, okay? They didn't put anything inside. They say now this system is operating at depletion. Okay, then I'm going to stop here, and this is P suction to the compressor. The compressor, I'm going to remove it, and here I have P discharge. Okay, so what will be a strategy? I propose to say to do counter current calculations from here to here. Okay, to calculate with the given rate, I have the total rate of the system. With the given rate, I have separator pressure, and then I can calculate pressure at the discharge of the compressor. That's nice, okay? That's no issue. Now what happens here? I know that the total rate is Qt, but how do I calculate the pressure at the suction of the compressor? I have two ways, okay? I can calculate it from here, or I can calculate it from here. So which one should I use? Are there two suctions at the pressures at the suction of the compressor?
No,
There are two, do you think?
No, one junction.
There should be only one. So really what's happening here? Okay, what if I tell you I have to change? I don't know. I know how much is coming out of here, but I don't know how much is coming from well 1 and well 2. That I don't know. Okay, that comes from flow equilibrium. Okay, so what I have to do is I have to say change these rates, these two rates, until I get the same junction pressure and I get this total rate. You see that or not? Yeah. So there is going to be only one. If I want to produce exactly this rate, and the two of them are going to be only in one point, they have to have one P junction. There is going to be a unique combination of this rate, that is the kind of the natural equilibrium rate, that will give me unique combination, Q1 and Q2 combination, that gives Q total, and also that gives Pj1 equal to Pj or P suction 1 equal to P suction 2. And we already have an idea how to do that, okay? With the solver we have, okay, that this might be a constraint and this might be the objective, for example. Okay, so you see, even though this system, it was something for design, I already give the rate, I still have to do some network, okay, because I know how much I'm producing up to this point, but then I'm not sure how this rate is split between these two. Okay, so let's try to do that in Excel. Okay, so what do we guess here? What do we have to give, like so first let's say maybe we can put, we already have the total production that we want is 28,000. Okay, that's going to be an input that I want to give. Okay, so let's, I didn't try it like that, maybe I will get into trouble, but that's why I have you, right, to help me. So let's say that I want to iterate with the rate, okay, to do that part of the iteration. But do I have to iterate with both rates?
No.
With two variables? No. Why?
You can calculate the second one from the total.
Exactly. Okay, I know that I have the relationship that Q1 plus Q2 has to be equal to 28,000. Then if I say I want to guess Q1, then Q2 is just equal to 28,000 minus Q1. Okay, so let's do that here. So I will guess with Q1. Okay, so that I'm saying that is let's say 15,000. So this is also a variable that is given, and this will be this number minus this number. Okay, after that I can do again my calculations. I have the rates, okay, that I'm not sure if they are correct or not, but we will see later. Then I calculate the flowing bottom hole pressure, IPR, that I'm doing co-current, okay? IPR, PWF, and formation, reservoir pressure, the rate, that is actually this one here, 20 bar. Can something happen here? Okay, actually this rate, what was the maximum rate that we got with 0?
10,000.
Okay, 10,000. So that value is too low. Okay, so that's an issue with this thing. So we put this one has to be bigger, right? 20,000. Doesn't like to cooperate. Okay, I'm going to get into trouble in this exercise. Okay, let's try 17. Oh.
We'll always account.
Okay, you did it already?
No, I mean, we don't need for the solver. Because there are too many choices.
No, well, we are giving this value. That's what we want to produce. These two. So maybe we have to put this one a bit smaller. Maybe. Okay, maybe we put it too big. But let's see. Okay, so we calculate co-current all the way to the flowing bottom hole. Then we go to the wellhead. And the wellhead has tubing P1. Tubing P2. Okay. And P2, that depends on the CT, on the S. That depends on P1. That's flowing bottom hole pressure. And that depends on this rate. And I'm relieved that didn't go down too much, okay, because the rate is too small. Then I have to continue. Okay, actually this one also should be in blue. Then I have to continue, okay, because I cannot stop at the wellhead. My system actually, now I'm here for both wells, and I have to continue to the junction, okay, or to the suction. So let's put that P suction, and that will be so that's line P2 again, and here I think is the C of the flow line, the inlet pressure, and the rate again. Woo, and it didn't go down too much. And now we know that these two should be the same. Okay, for that we have to use a solver, but let's wait with the solver. So now what else can we calculate? We can calculate P discharge, right? Because so far we have reached up to this point. Okay, we still, of course, we haven't done the equilibrium yet. We don't know how much the rates are partitioned, but now we want to calculate the P discharge. That one is easy. So I go and say P discharge. That's also in bar. Counter current, yeah. And I say line P1, and this is going to be this coefficient, this pressure, and this rate. Okay, 29. So you see here now that I need a compressor actually if I want to get this rate, because my discharge pressure is greater than the suction pressure, right? Just wait for a moment. Yep, need a compressor because this P discharge is much greater than P suction 1 and P suction 2. Yes?
Discharge pressure is required.
Is a required pressure at the discharge of the compressor. So I'm doing calculation. This one is counter current. Okay, so this number is not going to change, right? So what do I have to do now?
Solver for P suction.
Solver for
P suction.
P suction to be equal, these two numbers to be equal, okay? So for that, remember how we have done before, I calculate a P average, that is this plus this divided by 2. Okay, and now I say here error, and the error is going to be in bar squared actually, and this is going to be this minus this number blocked, then squared, then this other number, I don't want to have too many digits, okay, and now finally I can put here the sum of the errors. That will be the sum of error of these two, and actually the errors are the same, okay, but they are the average pressure is in the center and the two one are on the sides, are on the greater and lower than that. So I let's try if it works. I don't know if it will work. If not, you will have homework. So I say solver, please take this cell to a value of a minimum. That works for me. By changing just the rate of well 1, okay, then the rate of well 2 would change automatically. And really we're not doing anything with, so let's see. Okay, it works. Woof. So we are still producing the same rate, but that tells you that this will actually, the initial guess was very good. Okay, we assumed 18,000, and actually we're producing 18,200. And now the pre-suction is equal. And what is the delta P of the compressor? It's equal to this value minus this value. Okay, that's the compressor, that what the compressor has to bridge.
Isn't it minus 21?
Minus?
It should be the suction minus the discharge, or
Well, the compressor you all the time say that is giving pressure. So for the choke is the opposite. The choke, the purpose of the choke is to reduce pressure. The purpose of the compressor is to boost pressure. Okay. So Excel didn't embarrass the professor. That's good. Okay, so we use the solver to change this cell here. Okay, we have only one cell because we were using an extra equation that we had, that the rate of this well is equal to the rate of this well, the total rate minus the rate of this well. Okay, to drive the objective function, this cell, to 0. Too many lines here. Set solver to change this number to drive to 0. Okay. Yeah, and we didn't do anything else. And that's how we got the pressure. Now you see the pressure at the suction, all of them are the same, and that's the way it should be. You should have only one unique suction pressure. Okay, but you see that the rates, they are split differently, and that's what is important. So in this case we have kind of a mixed system of, this is some kind of flow equilibrium, okay, and this is and this is fixed rate. Why? Because we haven't given any. If we fix the rate here, what happens is you say, no, okay, I want to have a compressor, but now on top of that I want to know to fix exactly what is coming from each well. That will give like a homework, which if you think about it really doesn't make sense, because you don't want to choke. For that you will have to choke, okay, to control the rate that is coming from each well. So really you don't want, in a system, you don't want to do choking and compression at the same time, because it doesn't make sense. You're losing energy. Choke is dissipation of energy, and compressor is giving energy to the system. So if you do the two things in the same system, really doesn't. It's okay to get exactly the rate that you want, but really doesn't make much sense in the energy with the energy consideration. Okay. Any questions? Okay, this part you won't have to do in this set of exercise, but you will have to do it later in one exercise that we have about planning subsea compression. Okay, we have a field that is very similar to Gullfax, and you will have to actually, you produce with plateau, then you have depletion, and then you have to produce at some point, you install a compressor, and you have to do exactly this calculation. Okay, so now I have given you the tools to solve the whole exercise, but the part on compression will be later. Okay, any questions? No? Nothing? Okay. There are many ways, okay? This is one way that I propose to solve this problem. But there are many ways, there are many ways to solve the same. You can put this rate like a constraint. You can iterate on the two rates, but then you say that the sum of the two have to be equal to a certain value. There are many ways to pose this problem in the solving. The thing is that you have to, when you solve it, you know that it's solved because these pressures, all of them are the same, and you're getting the rate that you wanted. Okay? Okay. There is also, I told you that so far we have been dealing with surface networks. Okay, that means collection of pipes, transportation pipes, flow line, trunk line, etc. that they take all the production to the processing facilities. But we also have another type of network. I think I'm forgetting something here. Okay, those are downhole networks that I just put this figure because it looks nice. Okay. Oh yeah, there is something else that I also wanted to tell you here. That I told you before that really when you are in depletion, okay, when you have no control, then you are forced, you have only one unique solution, okay? Sometimes the trick that the reservoir people or that the reservoir engineer can make, they say, okay, you're saying that we have, let's go back to our plot here. You're saying that we have a unique solution, okay? We have a unique combination of these two. So what I can do is I can just take a slightly less rate and operating here and a slightly less rate and operating here and be inside the area. I'm very close to the equilibrium point, but I'm still choking, okay? So then I don't have to compute the equilibrium. That's also one approach that is used by them. For example, they say instead of operating here to the full potential, they produce a bit less than that value. Okay? The problem comes with time. When you have depletion, then the equilibrium is going down and down. So they have to be updating all the time or taking that into account. And that might be a problem. How they are predicting it and how the production engineer are predicting it. Okay, now, I remember now what I wanted to, very important comment. So I want to make a short comment about how to define well production scheduling. That means how to determine how much each well is going to produce. Okay? how do we, if we are in a design phase of a field, how do we define how much, okay, we want to produce so many barrels from this well, so many barrels from this well. How do you find out this number? Okay, and there are really two, as you already know, two kind of separate phases. Okay, you have one that is plateau. If we are working in a plateau mode, or if we are working in pure depletion. Okay, this is what we call mode A, and this depletion mode is what we call mode B. And there really is very different the way we deal with wells in the two modes. So how do we deal here in this mode? How do we distribute the rate in mode A? The ideal will be, let's say I try, that will be from the reservoir simulator perspective. I have the Q of the field versus time, and then I have a plateau and a decline. Okay, and that will be with my option 1. For example, producing with certain ratio. But now I try another, and then I get this number 2, then I try with another one. Okay, these are with different well offtake. So of course here the decision is obvious. Okay, we are going to take or choose the alternative that gives us the plateau, the longest plateau. Okay, and how do we find which one? So now comes the real question. Okay, that's very nice, that's what you say, but how do you find this option, the third option? How do you find it? Okay, so one way people use, and that has been used so far, is that you say that every well has to, the potential has to reach the plateau level at the same time. Every well has to, all the wells have to be open choked at the same moment. Okay, at this point, all wells should have open choke. Why? Because if there is one well that finishes plateau early, okay, let's say here, then you are going to begin to have a decline in the rate. Okay, so you want all the time to, at the beginning all of them are choked, all of them are choked, all of them are choked, and then fully open, and that's where the plateau finished. So you try all the wells that will enter into decline at the same time. So that's one approach. Try for all wells okay, that's the idea. You try that all the wells enter into decline at the same time. That means open choke. Okay, when you're producing in plateau mode. Okay, so how do we do that practically? How do we manage to, to honor this sentence? Okay, the way the people designing that, these are working with reservoir simulator. Okay, so the way they do it is what I explained a bit later before. Let's say from the reservoir simulation side. Okay, they have, I will try to make a sketch that won't look too horrible. Okay, you have your reservoir model, and let's say that we have 4 wells. Okay, let's say we have one well here, one well here, one well here, and one well here. Okay, well 1, well 2, well 3, and well 4. And I told you that every well in the reservoir simulator, every well has a boundary, has 2 conditions. Okay, in the reservoir simulator, needs 2 inputs at the boundary. Okay, they need, one of them is the minimum flowing bottom hole pressure. Okay, and they need a target rate. Okay, and I told you that in every step, in every time step, the reservoir simulator first tries first with the PWF, okay, in the boundary. Okay, it goes and applies that pressure in the well boundary. Okay, does the calculation, and then it calculates a maximum rate. Okay, Q max. And this Q maximum is what is referred to as the potential, not our potential, okay, we are a bit smarter in potential, but is the potential from the reservoir simulator, open flow potential. Calculates the maximum rate, and this is what we call, or reservoir simulator people call, is that how you call it? Reservoir simulator guy? Yeah? Or you just call it potential?
Yeah, it's the potential.
Yes, the
No, open flow potential?
We can call it absolute open flow potential.
yeah, absolutely.
But absolute is when you have atmospheric pressure.
Yeah.
And when you put the minimum bottom hole pressure?
Yeah, it's just the field potential.
Okay. So let's not confuse, okay? Let's put open potential, even though looks like it's called also potential. Okay, so and that's what's called the potential of the well. Okay, how much the well can produce. Okay. And I told you, okay, the story is that if this Q max is greater than the rate, let's put that story here. I think you already have it. But if Q max is greater than Q that I'm giving, then I produce Q rate, okay? But if Q max is actually less than the Q that I have specified, then I produce Q max, okay? Because I want to get all the time as much as possible from the reservoir. Writing kind of okay. So okay, but there is something very important about this potential. This potential is used, then what the people say is how much I want to produce, what is the total production of the field. The potential, the well potential, is used to split the plateau rate between wells. Okay, and how do we do that? Okay, so we have the Q potential of the field, potential, is just equal to the sum of all the potentials for each individual well, okay? From I equal to 1 to n, where n is the number of wells. Then you can calculate a factor for each well, that you can say this factor for each well is equal to the Q of the well, potential of the well, divided by Q of the field potential. Right? And then you say, if I have everything is operating at the minimum flowing bottom hole pressure, then I will get this split of rates. So I'm saying that this minimum rate, this minimum bottom hole pressure represents the back pressure of the network. Okay? Appropriately the back pressure of the network. So I say if I want all of them to reduce their potential at the same time, so that's the split that I'm going to use. I'm going to say that the actual plateau rate, sorry, Q of the well that is going to produce is actually the plateau that I really want, okay, that is much less than my potential rate of the field, times this xi. So we use the potential to scale and see how much each well is going to produce. Okay. Of course, remember the potential change from time to time. So some people do this at the beginning. One approach is to do this at the beginning. And never change. Okay. That means that with this factor you determine, okay, this well should produce 10,000, this 5,000, this 6,000, and then you don't change that number anymore for the life of the simulation. Or some simulators, what they do, and that's what the Deer Eclipse is doing, they calculate the potential at every point in time, and then they do a re-splitting. Okay, do at the beginning and never change, or they calculate potential at every time step, and calculate new well rates. Okay, maybe one well is declining very fast, so its potential is declining very fast, so you have to update that in every time step. Okay, so that's one way that I split the production, the plateau rate between wells, and that's the way it's done traditionally by reservoir engineering. Okay. Now, what problems do you see in this approach? Now that you have had the whole lecture in networks and you have calculated, so what really is important here? How much the well can produce doesn't really depend, doesn't stop at the bottom hole. Okay, but you have to see also to look at the whole production system. So another proposal using the production network is actually find the open choke flow rate of every well. Okay, let's say you have again the same 5 wells, okay, that were something like this, 5 or 4? 4. Okay, you commingle them together and then you have a network. Okay, and then you calculate open choke rates. Okay, you first have to transport, you have to bring the IPR here, you have to bring IPR from reservoir model. Okay, then at that point you run an open choke simulation. Okay, you calculate the equilibrium, open choke rates, and we call that QI, open choke, OC. And then we calculate another splitting factor, in this case of the production. Okay, a splitting factor that will be Q of each well divided by the sum from I equal to 1 to n of this Q OCI. And then we split based on this factor. And this is a bit more accurate procedure than the one just using the potential from the reservoir simulator. Okay, because this one really is taking into account the pressure drop that you have in the lines that you have in the well all the way to the separator. The other one is just using a fixed value. And I told you that using a fixed value doesn't represent, because you have all the time it's an intersection. It's two nonlinear equations that you're intersecting, and that point, the way it displaces in time is not exactly flat. It actually has a curvature. Okay? So that's one application of network, to split. Okay? And that's what actually GAP has this proposal. Okay? GAP is a software for network simulation. And is using this splitting method. Okay. Eclipse, if you use Eclipse, they use their own method and they have different ways that they can control everything. Actually, if they see that, for example, one well is producing too much water, they have a way also to penalize that well and increase the production from some others. Okay, because remember, also all the time we are concerned about the associated products. If it's an oil field, we are concerned about production of gas and production of water, and if it's a gas field, we are concerned about the production of condensate and the production of water. Okay. GAP is a software for network simulation and is using this splitting method to split the rates. And now we go to this is approach that is maybe you in your generation you will have to use that, and some people are using actually model-based optimization to try to find out the best rate. Okay, so that's kind of the future, and that's what people, more and more companies are doing it nowadays, and you have to be aware of that. Some people use model-based optimization to define wells production schedule. And that means what? That means that they have, this is the input. Let's say that here you have your reservoir model. Okay. Should take a picture. Let's not draw this. Let's take a picture. That looks too complicated. This one maybe? Do you like this one? Yeah?
Yes.
Looks kind of strange. Okay, so you have your model and you give as an input to this model, you give the rate of each well with time. Okay, that will be some kind of a vector. Okay, rate of each well with time, and then at the end you compute, you run the whole simulation live, run lifetime simulation, and then here at the end you compute recovery factor, cumulative production, we call it QP. Okay, so then I put on top of that, I put an optimizer. I put here an optimization engine. Let's put it in another color. Optimization engine, just like the solver, okay, just like our Excel, but has to be a bit more sophisticated. So optimization, okay, we put it here, and then we say please change this input, change the rate, okay, or the profile, or how much am I splitting or giving to each well to optimize or to maximize recovery factor and cumulative production. Okay, I put something on top of it that is going to try to do the work for me, the work that I was supposed to do, that we were doing before with some other kind of strange methods, because all of these methods, they base that I want them to finish at the same time. Okay, and I can use network, I can use reservoir, people argue which one is best. But this one is actually saying, okay, I want to use a mathematical procedure that is going to tell me in which direction or exactly which values I have to use to get here maximum recovery and QP. Yeah?
Is this gap?
No, this is, well, that's another session also, but just to give you an example, that could be resolve. Okay, there is another software called IAM. So this one usually we do with integrated asset modeling software.
Okay.
Okay.
Because how is it possible to specify QI at each time? I don't think in Eclipse
It's possible.
at each.
Yep. Integrated asset modeling. Okay, software. So for that we use Resolve. IAM is a product by Schlumberger, or we could use also Pipeit. That's a company here in Trondheim. Okay, for that we have to use something like this. Okay, so that's one approach, more complicated, but we leave, we take that decision out of our head. We can sleep well at night, but we just have to set up the optimization and see, okay, if it runs and it gives kind of coherent results. Yeah, and this potential idea, you can really have it either from Reservoir Simulator, or you can also have it actually for big fields. It's done with Reservoir Simulator, but for small fields, maybe you do it by well test. Okay, you test the well at open, no choke, you get the maximum rate that it has, and then you do the same thing. You do the splitting, calculate the splitting factor, and then this is the factor that you use to allocate rates. Is that clear? Yeah. Okay, then for depletion. For mode B, really the rate that I can produce from each well comes given by just the flow equilibrium. Okay. And for that is particularly important the network. Okay, for that the network is the one that is going to tell me how much I'm going to produce from each well. And the idea, of course, the purpose here is to produce as much as possible. So I want to put things that, for example, multi-phase booster, compressor, I want to maybe to put a bigger pipe, I want to, for example, add more wells to the system to be able to, so it will produce more, okay, more at that given stage, to increase its potential, okay. But also something else that we didn't consider is that the associated products like the gas, GOR, and water cut, they increase with time, okay, and can overload the processing facilities. Okay, that means if I'm producing too much gas, maybe I won't be able to process that. I'm producing too much water, I have a limitation. So in that case, I might choose to choke some wells that are high water producer or high gas producer, okay, if I think it's relevant. So in this case, I decide to choke wells that produce too much water or gas, okay. And for that also we could use some numerical. You solve the network, but then you include a choke, for example, for those wells that are bad, and then you choke them to try to, to just like you add a constraint in the solver. Okay, you say that the water production cannot be greater than certain limit. I think we have delayed too much the break, right? We have to have another break. So let's have a break and come back for the last part. Continue, just some energy, people. We are not about to finish, but I hope to make it short. Okay. So so far first that part is clear before what we discussed. Okay, division, or how do you split the rates in a field, especially in plateau mode, is a big issue. Okay, and how do we do it? Different ways, different approaches. Some people like to use optimization. That is something that is very trendy now. Companies that they run this they look like quite high tech, that they have done their homework, have done multiple times and see which one is the best. But so there are different ways to do it. But when we are in depletion, remember we have a unique solution. Okay, We might decide to, if we get too much water, to close or begin to choke one well or begin to choke another, or maybe put some boosting, but at the end we have a unique solution. Okay. Now networks, we can also find downhole, okay, like you see in the case here of deviated horizontal with a lot of branches, okay. So in that case we have exactly the same case that we had from, okay, we have inflow from here, we have inflow from here, from different areas, and they are commingling. We have almost the same thing, a branch structure, a tree-like structure that is being commingled, and actually you have here one junction, one more, okay? And in that case, the same things apply that for networks, okay? We have actually to solve a system of equations. Like in this case, this is a multilateral wall, maybe trying to reach with the same wall different areas. Or we have this one that where you have vertical different layers, okay? And yeah, you're producing just all of them through the same well. Also, with the case with networks, remember that I told you that it's not only the productivity of the layer, but also the distance that it has from because everything counts, okay? It's like the resistance that the well has from the formation all the way to the processing facilities. If the pipeline is too big, is too long, the diameter is too small, if it has, for example, accumulation of solids, then it's causing an extra back pressure. So everything matters in that case. And also in the formations the same, okay? Maybe you have a upper formation that is maybe has a high productivity, but the pressure is low. And this one here has a high pressure, but the permeability is very low, okay? So in that case, it's like you're producing with two, it's like you are, let me see if I find the picture. Stop that. Yeah. Okay, so that's what the theory, that's what we want, okay? That the two of them, the two formation, three formation, they will be the same, exactly the same. They're depleted at the same time, at the same rate. Everything is smooth, okay? We have a nice life, okay? And that's actually what the Bible tells you, what they recommend. How to split the choke? That's how you have to do it. All of them should be equal. Unfortunately, you get situations where this formation is nice, okay? Low reservoir pressure, but high productivity, high permeability. This formation has low permeability but has high reservoir pressure, okay? And they will be depleted at the same time. And maybe at some point you will see that some production even might go from this side to this side, okay? Depending on the network. You can also have backflow in the network. In pipes, it's slightly simpler because we might have also in the wells we have a check valve, something that impedes that the rate goes on the opposite direction, actually goes in the well. But when we have these systems downhole, then you might happen also that you don't have anything that blocks or that impedes that that kind of dictates the flow direction, okay? So that's a limitation that we have to live with. So that's the right way of doing it, okay? Let's see, so also you see, okay, you have multi-branch, you have multi-layers, okay, so that's a multi-branch. Okay, and that's a multi-layer. Okay. But you also might have, if you have one single wellbore, you might have the same situation, like in this case, okay? Usually when in this well where you have a pressure loss, okay, the pressure actually at the toe is greater than at the heel, okay, and then you know that the flow comes is by the difference in pressure, okay. So you have here a certain reservoir pressure that is uniform, and then you have a delta P that is bigger here than here. So actually you will have more flow close to the toe, close to the heel than to the toe, okay. And in that case also we have some kind of a network. Okay, and then you get this nice, yeah, so that's how you model it. if you have a very long wellbore, so then you have to begin and split it in pieces, okay? And then you have to say each one of them is producing something, and I have different delta P, and I want to calculate how much is coming from each formation. So that's a way to convert kind of a continuous problem into a discrete problem with different areas. Otherwise, this thing might happen. Okay, that you have, if you don't take any control, then there will be depletion, and actually you have gas coning or water coning at the heel. Okay, and not only that you have multi-branch, that you have multi-branch or multi-laterals, or you have also long horizontal wells. You might also have a lot of equipment inside the well. Okay, that is what we call inflow control device or inflow control valves. Anyone heard of that before? All of you? Okay. Things, toys that we put nowadays, most of the wells in the North Sea, they look like Robocop. Okay, they have so many things, have so many toys that they almost look like a machine. They look like like a robot. So here is one example, and this is what I tell you that we had this discussion, downhole chokes. Okay, in this case we have three. We have a donkey, and we have this ass, and we have a horse, and then we want to make all of them equal. So for that we have to install something to bridge or to control the rate in each one of the layers. Okay. So we have, let's see, what other picture do I have here? So that's a typical, that well actually I think is from Alfheim, a field here in Norway, that has 3 laterals. Actually these 3 are all of them horizontal in the same position, and they have this inflow control device. So this inflow control device, how does it look like? ICD, that's the abbreviation, inflow control device, or we have also ICV, inflow control valve. Okay, and the difference is that this is a passive. That means that it's like a positive choke. Okay, the opening is there all the time, and you will get certain the behavior, the opening is fixed. Okay, it's like the equivalent to a positive choke or to a bean choke. And you have also active, where actually you have some regulation, you can regulate. So how that monsters look like? Actually we have one. Okay, we have one in the lab, so if you want to see one real size, if you're curious, you can go and take a look. Okay, so actually it's something like this. You have a mesh that impedes that the sand particles go inside of the wellbore, because they will cause erosion, or maybe they accumulate in the wellbore and then they restrict the wellbore. Then it goes through some passages where actually this one creates a pressure drop, creates a resistance, and then you have some holes in the tubing, and here again you have flow. This is from the formation is outside. Okay, the formation is here, and here goes all the way to the wellhead. Okay, and these are passive actually because I don't have any regulation. The openings are there in place, and they produce certain delta P. So if I, for example, have a very strong formation, I don't want to produce so much of it, so I put a very small orifice. But then I have a very weak formation, so I put a bigger orifice to be able to control, to see how much is coming from each formation. This is another type. Okay, you see that you can have this, and you can have this opening that is causing the pressure drop, or you can also have this. These are more kind of typical nowadays, that you have the screen, and then the flow has to go in some kind of path through this helical channel, and then it's causing some pressure drop. And then you have the holes to go inside and then to be produced through the tubing. More pictures. So this is, for example, you have here a seal, okay, and you have 3 areas separated, and you need for each one of them a different resistance. Okay, one of them has high permeability, because the problem is if you produce too much from one, maybe you are creating too much back pressure on this formation. Okay, And that's something that you don't want. You want to produce equally, usually, from all of the layers. That's a nice figure, right?
So we can have the same sink for injectors, right?
Yep. Mm-hmm. Where am I? Okay, so that. What else do I have? Okay, so these are types that you have. This is called helical channel and this is called nozzle type. The two types that we already saw before. One of them is flow in an orifice. Then you have some other types. So these are passive, okay, because you don't have anything actually to control. Okay, these are passive. And then you have the ones that are active that I can actually regulate. And this, I think I might have a picture. Okay, so this is the one that we have in our institute. Actually, we don't have it here anymore, but we have it here just in the floor. So those of you who want to look, you can just ask to our mechanics if they can let you in, and you can see actually, and it's real size. Okay, so a well bore of 1 kilometer. So it's quite long. This is like 6 meters. So those are the things I think you, like a student here at NTNU, you should also use all the facilities that we have here to learn. So that's okay, and it's difficult to see how it works. So here I have another figure. And actually what you do is you okay, and that one is active because actually I have regulation. So I have a piston that is moving. I have one outer cylinder, which is this one outer conduit, that is this one, that is in contact with the formation. The formation is out here, okay? And they have a port where the fluid is supposed to come in. And inside of it, there is another one that is also has the capability to move. And with the hydraulic line connected to the surface, I'm able to move up and down this other cylinder. And then I put, depending on how much restriction I want, I put, for example, if I want a very small restriction, I put only these two holes in front of the opening. If I want a very big opening, or if I want almost no restriction, then I put all the holes in front of the screen. And then I can regulate that just like a remote, okay, just like a robot from the platform. I can say, okay, I want now this 30%, 60%, or 70% opening. Right? But you know, you think about it, this is expensive. All of this equipment that you put in the well, this is more or less standard in the North Sea, things that the wells have to have, but they are expensive. Each one of these things, to install it in the well, it's quite expensive. Okay, so this is active, and this is an old ICV, and you might have some newer models now. So if you have time, please look here at all the details. So there are some things that you have to lock them in place. Once you move them, they have to be locked in place, because when the flow begins to move through it, then you have vibrations, and you don't want it to shift from one position to the other. So you have this collet, and you have some ope holes here, and that's how you lock it in position. But if you put enough pressure on this cylinder, then it's going to move and go and lock in the next hole, and so forth. Anybody work here before with these ICDs? No? Just to tell you that exists in the well. And so another type, and that's going to be the last time, and with last type, and with that we finish. So we have also something called autonomous or self-regulable control device. Okay, ICD. And that's like this case, for example. That's actually Statoil is very proud. It's kind of their baby, and it's a valve that when you have the flow of oil, for example, oil has a low density. Okay, so when you have flow of oil, then nothing happens. Everything is flowing okay. But when you have flow of water, then this this plate goes up and then actually closes the opening. And then you don't have any more flow of water from that area because water is on the desired phase. Okay, so it's self-regulatory in the fact that you don't have actually any input from outside or any input from the surface, but actually when you have flow of water here, it's going to close, it's going to go up. Okay, because yeah.
How does it know that it is water? Pressure?
Long explanation or short explanation? It's because of the pressure drop in this channel, okay, in this throat. Okay, when you have a different density, then they tend to. I can bring actually. I have one in my office. This is a principle. I don't remember but I have. If you just make the experiment, you can build it maybe yourself. If you you put a pipe with this shape and then you put a disc below it, okay, and then you blow, you will see that the disc doesn't fall, it's just sticking. Okay, I will try to bring that and show you next class, okay, next Monday. So it's because of that. So it's going to fall if you have oil because it doesn't have enough density, but if you have water, then it's going to stick up.
So it is, for example, it is calibrated to pure water. For example, we have like a little bit increase of water cut, or we had just water break. So let's say we have 20% of.
It's the density of the mixture. So they calibrate it with some density of the mixture. When it reaches certain value, more than 80-90%, it's close. But something that still they're having some wells they're testing, but it's coming there. So just to give you the name, autonomous inflow control device. Okay. But in that case, for our modeling, really doesn't care much because this is only on and off. If we have water, it works. If we don't have water, then okay, it's just a restriction. Okay, this is like actually all of them are just restrictions. Okay, if we are going to build, for example, the system for, and that's how it's done. Okay, for the calculation of all of them. For this case, for example, we have an IPR. Then here we have another IPR, and here we have another IPR, and then flow from here to here. We have a restriction. We have is like pressure losses in a pipe, pressure losses in a choke, okay, and then we have again pressure losses. So actually, we can represent this system like IPR. Then you have a restriction. How do we put the restriction? Something like this. Okay. So we can actually use kind of a choke equation in this point. So this is the analog. Okay, and then here we go to the wellbore. So again, we have to do solving. Okay, we have to assume a rate through each one of them. Maybe we will do one example, or that will be the homework. Okay, so you have to assume rates for each one of them, and then you have to say that the pressure here is the same if I calculate it from here, or if I calculate it from here, or from here. Basically, the same thing as a network. You have to solve the network to find the operating rate. Yep, I think I don't have any more nice pictures. Okay, I think allocation you leave it for next week. So maybe to summarize, so we saw today one example with networks. Okay, so we saw three cases. We saw natural flow, that there is a unique solution, and I showed you how to calculate this unique solution. Then we said fixed rate, and then we have to calculate choke opening. And then we saw one case with boosting that was kind of half and half. One part of it was natural flow, and the other part was fixed rate. Then we have seen this part about how do you split rates. That is actually very important, and you have different methods. And I tell you that the network usually is a better approach because you're analyzing all that happens downstream the well. When you do it with the reservoir simulator, you have to use a very good value of PWF minimum that represents the back pressure of the network. And finally, we saw also that we also have downhole networks, and also we have to deal with that. So that's another complexity that you have to be aware. Actually, there is a software. The only software I think that does this kind of calculations is something called NetTool, and that's from Landmark, I think. Weatherford. I'm not sure. I have to check. I think maybe Landmark. Okay, so that's a specialized software to calculate downhole networks and to be able to design, because you can say if you here calculate the rates and you see that they're not uniform, then you can put another device with another opening or with another constant here, and then you can see if you get the rate that you want. So that's used to design your completion design. Yeah, and that's all. So before we close, any question? Crystal clear? Yeah. Okay, so we close the session. Thank you.